Good afternoon, everyone. Thanks for joining this webinar brought to you by Gebear, clearly. I'm Alistair Wallace, the UK Marketing Director for the company. I'm just sort of hosting this, and I'll be managing the Q&A later if there are any questions. So we've got with us Andy Lee, our Vice President of Engineering. Hopefully you can see and hear us okay. In fact, I wonder whether if you can hear us, if you could maybe someone put yes in the chat, that would be helpful. Yes, there we go. Thank you very much. All right, brilliant. So Andy, I'll hand over to you. Andy's going to run through the slides. There's a couple of videos, and then we'll have a Q&A later on. So Andy, over to you.
Okay, thanks, Alistair. So today's webinar is on asset ground improvement for structures in infrastructure and building space. So let's get into it. So who is Gebear? Just a quick introduction for those who don't know who we are. We are a leader in non-disruptive solutions for foundation and infrastructure settlement and substance problems. It's a global business established in the early 1980s in Finland. The company was then known as Eurotech until 2017 before a global rebranding as Gebear. UK business was established in 1989. We have offices in London, Wolverhampton, Winchester and Sandy. We have a full in-house design team, but we also work with third-party consulting engineers and material testing laboratories. And expansive geopolymers have been successfully implemented on more than 250,000 projects worldwide to date. So just a quick view of our footprint. As you can see, USA, UK, Sweden, Finland, Poland, China, and in the Gulf, UAE. Although the largest part of that business is in the UK, but all other parts are expanding. So what sectors do we operate in? Well, we're in highways, commercial, residential sector, energy and utilities, airports, ports and harbours, and railways. So all of these areas that suffer from subsidence-related issues or settlement-related issues, we have ground improvement solutions for those types of sectors. Now, a very, very brief overview of our capability, just to give you an idea, general idea. So these are the sorts of things that we aim to do with our technology. So we're looking at increased loading. That's a bearing capacity improvement. Settlement mitigation, settlement being one of the key factors for the performance of structures. Slab pavement stabilization and lifting. Re-leveling buildings and lifting buildings. Transition zones, this is ground improvement near to structures. Clay shrinkage treatment and substance mitigation. Void filling, water exclusion, impermeable barriers. These are reducing water flow. Slope stabilization, deep soils compaction, liquefaction mitigation associated with earthquakes. Compensation grouting, this is for tunneling activities. Vibration reduction, containment of mobile contaminants in the soil and groundwater, and structural stabilization. They're the general areas in which geopolymer technology can be applied. There is a detailed capability statement on our website, which gives a lot more detail in terms of what are the limits of certain systems in certain scenarios, and that can be seen on our website if people wish to go and have a look at that. But if I was just to tell you in a general case, well, what type of soil can you treat? Well, pretty much any type of soil. So whether that's clay, sand, silt, made ground or natural soils, there is really no soil we can't actually treat. The only soil which is more of a challenge is organic soil, peat deposits. Due to the nature of these soils with very high moisture content and high organic matter content, we need to use a lot more polymer than against normal soils, which are made out of clay minerals and silica, etc. But essentially, most engineers run away from made ground when they see it. We sort of run towards it. So anything to do with very poor ground, particularly made ground, where there's low bearing capacity or settlement issues, this is an area where we can directly help you. As I said, the capability matrix can be downloaded from our website, where you'll get a clearer version of the copy. So let me just introduce you to geopolymer materials for those who are not familiar with them. So Gebear geopolymer is based on a multi-component structural resin technology, which is specifically developed for ground engineering applications. So the geopolymer comes to site as two liquids, which is injected into the ground. And when those two liquids are mixed together, there is an exothermic chemical reaction, which induces a state change from liquid to solid. It's a consequential increase in volume, which produces the dynamic energy and subsequent expansive force. The chemical reaction is very quick, and the immediate resulting solid compound possesses definitive physical and mechanical characteristics. Geopolymer reached 90% of its final mechanical characteristics in less than 15 minutes. So it's a very fast-acting ground treatment. So if you do this sort of ground improvement, you get almost instantaneous results. You don't have to wait for the material to cure, as you might do for cement-based technology. Geopolymer technology is very fast-acting, so it's very good in sort of emergency situations where you need immediate strengthening. Now, as a result of carefully selected, we have done over 30 years research into the development of these polymers. And we have a wide range of polymers for different applications to provide a safe and very accurate solution to any particular problem. There's a quick clip here to show the expansion of one of our geopolymers, which was injected into a void, to sort of show you how quick it reacts. So here you see the polymer going into the void, and after a few seconds, chemical reaction happens and the void is filled with geopolymer. So that video is shown in real time. That's not been sped up. So this type of geopolymer has a reaction time measured in less than 5 seconds. So once you've injected it into the soil, the reaction commences within 5 seconds and is probably complete in less than 10 seconds for this particular type of geopolymer. We have different ones which have much longer reaction times, which we would use in different scenarios. But if you want to fill something very quickly, this is a particular polymer we would pick. Now, we can show a simple graph here of what I've tried to describe verbally. So on this sort of graph, there is sort of two lines. One is an expansion line, and then there's a viscosity line. So what you can see is that on the bottom of this graph is the time axis, and we define certain time periods. So if you're designing with geopolymers, you need to know what's called the cream time. Now, that's the amount of time that the liquid is in its liquid state before the actual expansion starts. And that time is designed based on the sort of additives that are put into the resin, which control the time of reaction. These are accelerants. And that cream time will vary, depend on polymer to polymer. Now, after the cream time, the reaction started, and so you get this expansion of the geopolymer as it moves from a liquid into a solid state. And so as it moves from liquid to solid, there's obviously an increase in viscosity, so almost exponential increase in viscosity, such that when you reach what's called the gel time, a few seconds later, you've now got an expanded block of hardened polymer. There is a final time called the tack-free time, which is after the gel time, and that is when the polymer's completely solid, but there's been no further expansion between gel and tack-free. It's really just the final setting process. So that is the basic process that governs how we can design with the geopolymer. We need to really know the shape of these curves So we can work out how much a given amount of polymer is going to expand into the soil and how quickly it's going to happen. So we sort of need to know these things. So this shows you an X-ray cross-section using an X-ray microscope to look at the actual structure of the geopolymer. And what you see here is they look like bubbles. Well, in fact, that's what they are. They're bubbles of carbon dioxide, which have a skin of resin around them that contains the actual gas. So the driving force in the expansion is CO2. That's what's been released in the reaction, and that's what drives the expansion. And here you have resin around the edges or bubbles, and then gas in the middle. Now, as the bubbles get smaller and smaller and smaller, and the amount of resin goes up and up and up, then the polymer gets stronger and stronger, to the point where there's a small number of bubbles, in which case you've got almost solid polymer with no bubbles, in which case the polymer is at its strongest possible condition. So how strong does it get? Well, the strength of these geopolymers depends on their density. And we have a graph here of this. This is plotted up most of our routine geopolymers with their compressive strength on the y-axis versus their density on the x-axis. As you can see, that line is non-linear. But it shows that when we're at densities approaching 600, 700 kilos per meter cubed, we've got a compressive strength higher than 20,000 kPa or 20 megapascals in compressive strength. And I can tell you that the tensile strength is only about 10% less than the compressive strength, very similar in tensile to compressive strength. So that gives you the range over which strength can vary. So from the lower densities, it's less strong. At high density, it's have a much higher strength. Stiffness, and in terms of the Young's modulus, stiffness modulus, again, the stiffness of the geopolymer varies with the density. And that's because the higher the density, the less bubbles in effective terms. And so here we can see that the stiffness modulus at densities above 600 kilos per meter cubed is of the order of 450 megapascals stiffness. So that's the sort of maximum sort of stiffness. It can be higher than that. This graph could be extrapolated up to around about 1,000 kilos per meter cubed, but we generally have data up to about 650. So that's the general range we design within. People ask me about sustainability, and does using chemicals, these products are essentially made from crude oil, resins. Do they contaminate the ground? Can you pollute groundwater with this type of chemicals? And we've had these tested by independent companies, and we've had them tested on the solid material in blocks. As you can see in the picture, we've had these blocks ground up into dust and then tested in a leachate sense, mixing them with water, and seeing does any chemical partition out from the solid into the water, and then measure the water quality. And we've had definitive results back from Stantec, who were previously known as ESI, who demonstrated that there was absolutely no impact on water quality due to the impact of geopolymer, such that using geopolymers would not be deemed a groundwater activity under the UK environmental protection regulations. So it's safe to use over aquifers. We did further work on the sustainability, that we were asked, well, okay, that's in the solid state, but what about in the liquid state? Is it possible any contamination could come out of the geopolymers when you inject them in a liquid condition? Can anything come out before they harden? And so we did some testing, some leachate testing using a recirculation tank, or rather FLI did it for us, where we injected our geopolymer into a steel container full of sand and water. And we measured the quality of water within the sand over a 72-hour period to see if any chemicals were coming out during the injection process. So we essentially injected some liquid geopolymer into this tank and measured the water quality before and after, and then kept on measuring it over a period of time to see does anything change. And again, we had a similar result when they compared the levels of contaminants found, and they found that none of them exceeded the EQS, that's Environmental Quality Standard, for pollutants as stipulated in the Water Framework Directive. So testing these geopolymers under the most stringent conditions, i.e. in the liquid phase, there's no impact on groundwater. So they are safe to use from an environmental point of view. We've also interested in other aspects of sustainability about, what about the carbon footprint? The geopolymers, they must have a high carbon footprint. Well, they don't actually when you look at how you use them in the field. We had independent assessments done by Carbon Footprint Limited to determine how much carbon or CO2 equivalent do you use if you have a Gebear geopolymer underpinning solution versus a traditional underpinning solution such as a piled raft. And also we had a comparison against in the highway sector to do a concrete road bay replacement, and you could do geopolymer densification of the soil under the bay. That means you don't have to replace the concrete, and you could do the same thing in the rail sector on level crossings. And we found, or rather Carbon Footprint found, that Gebear solutions produce between 53 and 90% less carbon footprint compared to traditional grouting or replacement solutions. And that's looking at the whole footprint of the activity. So they do offer carbon saving as well as being sustainable. I just would like to say each year that Gebear calculates its own operational carbon footprint, which we offset. And we're a carbon neutral organisation. And we're actively seeking ways to reduce our ongoing carbon footprint each year. So how does it work? So the way in which geopolymer treatment works to improve strength, increase bearing capacity, reduce settlement, it varies on the type of soil that you're in. So in clay soils, the way the geopolymer works, it actually creates fractures in the soil, and along those fractures, geopolymer migrates and hardens, and it forms a network of interlocking layers of geopolymer. So you have hard, stiff geopolymer embedded in the soft clay, and that reinforces the clay, a bit like putting rebar into concrete. And in the pictures, you can see layers of geopolymer inside clay once an injection has been done. Just a brief explanation on what we call equilibrium pressure. So in order to sort of understand how strong your geopolymer is going to be in the soil, because that's something you would like to know, how strong is it? Is it 10 MPa? Is it 5 MPa, 2 MPa? We want to know how strong it is in the soil. You need to determine what's known as the equilibrium pressure, and that's the pressure at which the expanding geopolymer is balanced by the resisting force of the soil around it. And you can do that. There's a theory being developed, published by a guy called Manacero, relating to how you calculate the equilibrium pressure. And as I said, it's a function of the swelling pressure of the polymer, and it's a function of the confining pressure of the soil. And you can solve a bunch of equations and you can determine that value. And it will tell you at what pressure the polymer will be essentially freeze at in the soil. And that will define its density. And once you know the density, you can get the compressive strength from lab testing. So this is how you actually determine the strength of the polymer in the soil. You have to determine the equilibrium pressure. Now, there's a little bit of here on some ground improvement results. So there's on the previous one, I'll do a few more case histories before, but essentially we have done a lot of testing on sites using DCPs, or dynamic cone penetration testing, to see how strong is the soil before, how strong is the soil afterwards. Here's an example of a test case we did in Middlesbrough, where the blue line is the before treatment and the red line is the after treatment. And you can see here that the improvement in shear strength ranges from about a factor of 2 to a factor of 4.5. And the black dots on the graph is the model estimation of what the performance would be. And on this particular case, the average improvement was very close to the actual improvement. So something of the order on average of 2.5 times increase in shear strength for this particular case history on clay soil. In granular soil, we have a slightly different process in that we have permeation. So when you inject liquid geopolymer into granular soil, it permeates or moves through the pore space in between the grains, doesn't create fractures. So it permeates and forms a bulb, if you like, in the soil, sort of like a spherical shaped object, a bit like football, I suppose. And as the reaction progresses, that sphere expands in size to compact the soil around it. And it's that expansion force which basically compresses the soil grains next to each other to sort of densify the soil. And this shows it into a pictorial sort of slide. Sort of a stage 1 is you inject the liquid geopolymer. Stage 2, it starts expanding. And stage 3, you get what's called a plastification zone. That's as the polymer is fully extended, there's a zone outside where the polymer is that's actually all the soil grains have been pushed away, or rather pushed into each other, such that if there's an adjacent injection next to it, you sort of densify the soil in between the two injections, as shown on this picture. So by arranging our treatment in lines or in areas, you find that there's overlapping compaction from individual injections, and so the soil is densified in between the injection points. The soil's got nowhere to go. It's just pushed together, increasing the density, increasing the friction angle, increasing the bearing capacity, and reducing the settlement. So this is how it sort of works. And here's a few graphs of some before and after that from a particular site, just that show that the improvement you get will vary. Depends on how loose it is to start with, and depends how much you put in. The more you put in, the more densification you get. And the job of a designer is to work out, well, what's the minimum that I can use to achieve the desired outcome, which will vary from project to project. Now we've got an interesting little video to show you about some testing we did with Nottingham University on clay soils. So I'll let Alistair play this clip and let you have a listen while I go on to mute.
We're struggling to play this one, Andy. So if you want to carry on, we'll come back to this one after the slides, if that's okay. Andy? Can you hear me, Andy? Yeah, Andy, the video's not loading. So if you want to carry on with the slides, we'll come to that one afterwards, if that's all right. Can you hear me, Andy?
Are you playing the clip, Alistair?
Yeah, Andy, can you hear me okay? Can anyone hear me? Oh, right. So Andy can't hear me. Well, so this is strange. So I can't play the video, but Andy can't hear me. To tell him that. So let me just send him a little message. Sorry about this, everyone. This is just bear with us. Andy, can you hear me?
Yep.
Oh, right. There, you're back. You couldn't hear me then. I was trying to say the video's not playing on the on the YouTube channel. It won't flick to the video. So if you want to carry on with your slides for now, and then we'll try.
Okay, sure. Sorry.
Okay.
No problem. Okay, then, yeah. So we'll play that one at the end. So moving on, I've got a case history here regarding Hurst Castle. So this is a job we did for Historic England, and here there's a picture of Hurst Castle. Now, the origin of this structure, it was originally built by Henry VIII. The circular tower in the distance was built by Henry VIII, and then there was a gun fort built for the Napoleonic Wars, late 1700s. And inside each of these sort of square doors, there was a very large cannon originally placed. And through wave action, the structure had been undermined, obviously by the sea, and caused a sort of collapse. So we were asked what could we do to stabilise the rest of the structure, which was also at risk of collapsing because the soil had sort of washed away the soil underneath the foundations. So here is a treatment plan that we have. Now, this is in plan view. This shows you where we were going to do some injections along underneath the foundations to this part of the castle here and along the castle here. So this was the idea to what could we do to strengthen the soil underneath the foundations to this castle. Sections to be supported as shown. So this is an injection layout in cross section. So what you can see here is this is the sort of foundation, if you like, or the building, and the sea had eroded out. Essentially, it'd taken away the soil away from underneath the foundations, and the soil here was like a shingle, like a gravel on the beach, sort of gravel, and there's essentially a void here. And obviously, as that void was progressing under the building, it got to a critical state where it fell down in certain sections. So in order to sort of prevent that from happening on the other parts where there was voiding, we were working with a contractor who filled the void in with loose gravel from the beach. And our job was to then inject into that loose gravel and densify it in situ underneath the foundations to sort of create a new foundation under the existing foundations. And this is all done in the intertidal zone. So at high tide, the water is up against the wall of the castle. So that meant that we could only work during low tide. Here is a trial injection test that we did. This shows you what the sort of soil is like on the beach. You see these large shapes here. These are, in fact, bulbs of geopolymer. Where we injected into the soil about 25 kilos of one of our polymers and expanded to form a bulb of this size, which we've essentially dug this out of the soil to have a look at it. To give an idea of how much 25 kilograms would expand to. And in that expansion, it takes all of the gravel with it. So you end up with like a bulb of polymer and gravel, a bit like a concrete. It's essentially what it looks like. We did some field testing as well to see what densification we could get. So I'll come on to that in a minute. In the field execution, we had a mobile injection unit and a power pack mounted on a trailer. As you can see, the sea was here. We had to work along this wall here. We worked in the intertidal zone in 6-hour shifts. injection tubes are vibrated to depth at the specified angles. No drilling was permitted through the foundation because it's a listed building. We put in 120 tubes, and I think on this job we used about 2.3 tons of polymer to stabilise the foundation. Here is some test results we did on the trial section. The blue line shows you the equivalent SPT density before injection, so extremely loose soil here, sort of like 1s and 2s. And after injection, we were getting SPT blows over 14 like this. And the peaking here shows you the impact of the bulbs. So there was a significant densification of the soil due to the injection of the polymer. We also collected some lumps of the material, and here is a lump of the actual polymer mixed with the gravel. We took that to a lab to get it tested, and for this particular job, I think the average compressive strength was around about 3 megapascals compressive strength, which was sufficient for the load capacity of the castle. So all in all, that was a successful project. I've got another case history here from what's called the Gladstone Library. So what is the Gladstone Library? This is the UK's only prime ministerial library. It was built following a bequest from William Gladstone, Victorian statesman, 4 times Prime Minister of Great Britain. It's located in Harwarden in Flintshire, in Wales. The current building, it was raised in 1902, and it is a Grade 1 listed building. And parts of the structure were showing signs of settlement and cracking damage, and this is believed to be due to leaking water pipes in the ground. The soils underneath the site were basically silty sand, and leakage of water was causing subsidence under the property. Obviously, being a listed building, they wanted a non-disruptive solution to support the foundations. This shows you the areas that we did some investigations where the particular damage was worst. And then this is the starting SPT values. You can see that there was the density wasn't too bad. Here it's about 10 on average SPTN value. That's loose, medium, dense. But in the key areas, it was very, very loose, where the SPT was like as low as 3. So we had very loose soil in a localized area under the foundations, and that was causing the movement. So this is a problem we had to fix. We ended up with this is what a typical treatment plan looks like. We have injections at 1 meter spacings around the edge of the affected foundation. We install our injection tubes at 3 levels on this particular project. I think they're at 0.1, 1.1 and 2.1 meters below foundation level. And then we inject our geopolymer through the tubes to support the building. This shows you the sort of work areas we're in on site. And then this is the after results. So these are the before blow counts converted into SPTN 100. Sort of as we saw before, it is down as low as 3 before, and then up to 10, then back to 5. So not great soil, but the after test results, all of the soil was medium dense. So a substantial improvement in density. As we used a specific high strength polymer for this particular project, but the amount of improvement here was substantial, and the client was very happy with the result. So that was the sort of ground improvement on that particular project. I mean, the improvement there is probably 5 times the density increase, something like that. And then there's another case history here on the stabilisation of a sewer. This is a infrastructure-related project. So here there was a large diameter sewer had suffered settlement due to displaced joints. So the joints. This is an underground sewer where the joints became displaced, water leaked out of the joints, and that sort of led to fines being washed out of the soil, and that has led to subsidence of the overall sewer line, and that then led to the road surface subsiding and cracking. And so there was a major issue with the stability of the road and also the underlying sewer. So this was quite a difficult project to fix. You can't actually see where the sewer is. It's all buried. So moving on. So what we needed here was a lot more information as to what the structure looked like. Fortunately, the customer had a BIM model to help the design of the site. So we had a good 3D model of exactly where the sewer was underneath the pavement and where all of the associated services were, because there was, gas, electric, water, other services crossing the sewer at various places. So we needed a detailed BIM model to understand where we could put our injection points, because what we were going to do was inject polymer underneath the sewer to lift it and stabilize the soil directly underneath it. So that required quite a complicated model to understand where you're going to put your tubes. So this was what we came up with, sort of like in a 3D sense. 3D, we had to model exactly where each injection point was going to go to understand under what part of the structure was needed support. And one of the main reasons for this is to make sure we avoided existing services. We don't want to drill into gas mains and stuff like this. And so this drawing sort of shows the general outline of where the injection points were. At each injection point, there's probably several injections. And so we do that by extraction. We go down to the maximum depth, inject polymer, and then retract our injection tube and inject again until we've got the total amount of kilos into the soil to densify it properly. So that shows you the sort of modelling that is required on these sort of complicated projects. And then again, to verify performance, we've got some before and after SPT values here. And these sort of show that the SPT before treatment was almost, some places it was at zeros. I mean, literally no strength at all. Probably averaging about 2, SPT of about 2, maybe 3 average, which is very loose soil. And after treatment, we were probably around about 8 on average, 7 or 8, which again, that's a significant improvement and enough to stabilize the structure. That was looked at the sort of performance. We also had a look at some long-term monitoring using InSide technology. So we were able to get some satellite data points on the road above where the sewer is, and to look. And what you can see from the precondition is that there was a general deterioration in level, followed by a sort of catastrophic drop immediately prior to us doing the work. So that was a general trend in satellite elevation data. And then once we'd done our injections to lift the structure, we got an immediate rebound up. And then, although the data is moving around a little bit, it is essentially horizontal now. So it's maintained a level after we've done the treatment. So as far as the client was concerned, and this was Anglian Water, they were quite happy with that performance. It showed that the sewer had been stabilised, and they could then do their reconditioning work on a stabilised sewer. So that is the end of my presentation. I'm not sure whether we can still run the final video or not. I'll have to ask Alistair about that one.
Yeah, unfortunately, it's just giving me, you probably can't see this, a spinning wheel. So what I'll do is I'll send that video out on a follow-up email. It's a good trial video, but there's quite a few questions that have come through anyway, Andy, so probably could
we can spend some time on Q&As, not a problem.
Absolutely. So, right, let me just enable Q&A mode. I know loads of questions have come in. So hopefully these will appear on screen. Let's just scroll back up. So, Okay, so I'm going to start displaying these, Andy, if you want to start answering as well. If the geopolymer is used in permeable soil, is there a risk of uplift or heat from the injection? Also, if it's used for underpinning, how do the bulbs of the strengthened soil excavated all work?
Well, yeah, there is a risk of uplift, and so when we do the execution of the project, we monitor ground levels using a laser level to make sure that any uplift that occurs is within the specified limit. For some projects that we do that don't have a specified bearing capacity target, evidence of ground improvement is often the fact that the building's moving vertically upwards. And so if you can move the building up 0.5 millimeter, that's probably evidence that you've actually improved the ground, in which case you stop injecting. If sometimes the object is to lift a building, and so we need to lift it 10 millimeters, which case we need to monitor the building to make sure what lift has been achieved. So yeah, lifting is part and parcel of what we do. How much lift we get depends on what the objective of the exercise is.
Okay, thanks, Andy. So let's have a look at this one. Is the system restricted to use on remedial projects only?
Not necessarily. It can be used on greenfield sites. We just find our solution is often more cost effective on existing brownfield developments, existing structures, but there's no reason why it can't be used on greenfield sites. Certainly, you know, it can be used as a remedial measure on slope stability, things like this, retaining walls. Yes, so there's no non-restriction. It just comes down to a matter of cost.
Okay. So do we have examples of geopolymer on bridge abutments that have experienced settlement due to seasonal clay soil?
Well, we've got a lot of experience of clay shrinkage on buildings and structures. Specifically on a bridge abutment, I'm not sure about that. Bridge abutments, it could be a transition zone issue rather than a clay shrinkage issue, but it's something I'd be very interested to have a look at, because I think you can mitigate clay shrinkage on embankments. Same principle. We didn't talk about clay shrinkage in this presentation, as you know, Alistair. Yeah. We do that in other presentations that I give on mitigation of clay shrinkage, and that's not been covered today. But I'd be very interested to know more about that. So short answer is probably yes, but we didn't cover that topic today.
Okay, let's go back through. A lot of questions coming through, actually. So can solutions be used for domestic foundation settlement subsides? I mean, yeah, yes, in a short word, and Andy just alluded to it. We do a webinar about our solutions in clay soil specifically, which obviously form sort of 80% of all subsidence claims in the UK. But don't know if you want to add anything, Andy, to that.
Yeah, I mean, we do a large amount of work in the residential sector, social housing, residents, private resi, insurance. We do a lot of work in that area. So, and it's a very common solution for domestic subsidence.
Yeah, and we work directly for the insurers who appoint us, as well as social housing and private customers. So, if you've got an issue, Alan, or further interest, let us know. In relation to lifting a slab, how far can the slab be lifted, and what accuracy can you achieve for the re-leveled slab?
Well, I mean, we can routinely lift up to 200 millimeters, and we normally lift to a sort of an accuracy of plus or minus 1 millimeter, maybe 0.5 millimeter accuracy can be achieved. You could do more than 200 millimeters. It just costs more money because you need more polymer. So yeah, there's routinely up to 200 millimeters. You know, depends how much lift you want to correct for, but yeah, that would be what I would say.
Yeah, hopefully that answers that, Howard. Next one from Daniel. Are there any implications of removing tree roots vegetation from clay soil after treatment?
Yeah, these are people who should attend our clay webinar, I think, as all the answers are there. But there are, if you remove trees and roots from clay soils, then you're going to get heave as the moisture content increases in the soil. So you're going to get soil heave. So mitigation there is then we have a geopolymer solution for subsidence related to trees and clay shrinkage. I didn't cover it in this presentation, but we do have one, and certainly, yeah, you can mitigate it by changing the permeability of the clay soil with polymer.
Okay,
that's how you do it.
Yeah, definitely. Hopefully that answers that. And I'll send out. Well, we haven't scheduled in the next clay webinar, but it will be probably early December. But look out for that, John. Yes, I can upload a recording. And then, so what is the long-term degradation of the Gebear geopolymer? 10-year guarantee is provided, but after this period, do you expect degradation, loss of volume or strength?
Yeah, okay. So I think the 10-year guarantee we provide is essentially based on commercial terms. So, you know, the 10 years is probably what you could obtain in the market from other solutions. So we generally match that. But in terms of how long, what is the longevity of geopolymers? I mean, we have a BBA certificate for our treatment solutions, and that states minimum design life of 60 years. And I've seen research evidence and talking to our manufacturers who produce the polymers for us, they would say that the design life in excess of 120 years would be expected. The reason being is that geopolymer resins essentially comprise of polyurethane type materials, and they do not biodegrade. There's very, very few bacteria can degrade this type of material. So it's very long lasting because it's very inert, so it can't be degraded by bacteria. So that's why it's stable for a long period of time.
Yeah, and I guess in 120 years, if we needed to do a retreat or add some more polymer, that's completely viable. If we're still here.
Yeah, if you're still there, Alistair. Yeah.
Yeah, so
I probably won't be.
No, well, let's keep optimistic. Who knows? Chris, do you have any examples of use of geopolymer on bridge abutments? So we're sorry, we've come.
I think we had that question.
We did indeed, yes. Let me move on. Insurance back guarantee question. Are there any exclusions at retreatment? It's more of a commercial question.
That's a commercial question. I think we'd have to have. I mean, there are terms of the insurance back guarantee which are subject to terms and conditions of the quote and which is provided on.
Yeah.
Or can say all contracts have terms and conditions that need to be complied with. So we don't have to talk about that right now.
Yeah, no, that's fine. Drop me an email, Jason, and I can steer you towards someone that would give you a better answer on that one. Are geopolymer treatments environmentally friendly? David Stokes.
Yeah, I think I tried to cover this early in the presentation. I mean, yes, they do not impact groundwater quality in any way. And two, they generate lower CO2e footprint compared to traditional solutions. So on those two counts, I would say they are environmentally friendly.
Yep, and we've got reports on our website if you needed further details on those. And now, Rommel, how far sideways generally will the polymer spread from the point of application for each soil type?
Well, I'll tell you now, the distance to which the polymer will migrate is a function of how much you put in the ground and on the nature of the soil in which you inject it. Generally speaking, we set out our injection points at about 1 meter spacing on the average. And that's not, so that means that the polymer doesn't generally expand much more than 0.5 meter from the point of injection on the average case. Although it can go probably double that, depending on how much you put in and on the type of soil. But it's not going to be migrating tens of meters through the soil. It's literally about 1 meter. That's about as far as it can go through soil. Yep. You go a lot further through a void, but through soil, that's how far it can probably go.
Okay, hopefully that answers that, Rommel. Jason, is it accepted by building control?
Well, yes, as far as I'm aware. Now, we need to be careful what we term in building control. You know, does it fall under building control regulations? Well, what we generally do is ground improvements. So we're not changing the nature of the foundations, the design of the foundations, the depth, thickness or width of the foundations. So we're not altering the structure. So therefore, it generally falls outside of the building control regulations because it's ground improvement. We sometimes, if we're doing a ground improvement, we submit calculations to building control to show we've improved the bearing capacity. Yes, we can do that, but it doesn't actually sit within the building regs in terms of, because it's not a structural alteration. It's a ground improvement, and they're quite different.
Yeah, perfect. Thanks, Andy. Hopefully that answers that, Jason. And then Tom, how accurately can you control lift?
Well, we can control that, I would say, easily within a level of a 1 millimeter accuracy. We're very, very careful when we're lifting buildings. And if you're using fast-acting polymers, then the faster they react, the easier it is to control the lift, because as soon as you stop injecting it, you stop the movement. When you use longer time-acting polymers, it's less easy to control the lift, because when you stop injecting, the lift is still happening. But for fast-acting polymers, as soon as you take your figure off the injection gun or equipment, you essentially stop polymer going in the ground, and that almost immediately stops the lift. So, and we have very experienced technicians who know how to do this. And also, you need very careful monitoring, consistent monitoring to continually monitor what's happening.
Okay, and then Nima, do we need an MMO license for the injection? That's the Marine Management Organization. I've not heard of that. Andy, have you?
I'm not familiar with that. I don't know, but the point is the material we use is it will not generate leachates that affect water quality. So if this is something to do with, does your product affect water, then the answer to that is no. So that might mean that you don't need a license, but we'd have to understand what the terms are. So if someone wants to send that in, we can look at it.
Yeah.
And Nima sends that in, we can look at it and give you a proper answer.
Yeah, definitely. John asked, do you monitor adjacent third-party structures for deformation during ground treatment?
Yes, if we have to. It depends on the site in question. We would normally monitor party walls.
Yep.
So yeah, obviously we don't want to impact negatively on adjacent properties. So that's something we'd look at very carefully. Okay. And that's case by case.
Indeed, yes. Peter asks, does the polymer float in ground if grouting in water? So essentially buoyancy.
Well, geopolymer will float in water because it's less dense than water. But we don't generally inject into water. We will inject into the soil underneath the water. So in which case it is unlikely to become buoyant because of the sand that it traps. So that's not likely to happen. But if you did inject it underwater, it would float to the surface because it is less dense than water. But we generally don't do that.
No. Okay, hopefully that answers that, Peter. And then Tom asks if there's any information available on thermal properties.
Yeah, we have some information on file on that. It's a pretty good insulator. Geopolymers are quite good insulators because it's a similar material is used to insulate lofts, which people should be aware of. So people use spray foam to insulate lofts. They're not exactly the same materials, but they're similar in their chemistry, and they are good insulators.
Yeah, the principles are similar.
Principles are very similar.
Okay. Then we've got, in which way is polymer injection different to grout injections from Manuel?
It's very different. If we're talking about cementitious grouts, these are non-expansive grouts. So the way in which geopolymer works is fundamentally different. And we're relying on the expansive force of the polymer to compact the soil or to fracture the soil and create hard layers. Cementatious grouting is really just a volume replacement technology. It's really completely different. The two are not really comparable in how they work.
Yeah.
Almost completely different.
Okay, we've only got 5 minutes left. I can still see quite a few questions, Andy. So let's
All right.
try and rattle through these. Probably a good job we didn't have the video actually. So, has there been any use of geopolymer to fill cavities and voids in caustic limestone?
Yes. Short answer to that one.
Yeah. So if you want to
If
contact
you've got
us,
some voids in karstic limestone, they can be filled with polymer.
yeah. Has the solution ever been used for mine adit stabilization?
Yes. Simple question. We've definitely done this. I was looking at one of these jobs in Cornwall this week, actually, to do some mine work filling in using polymer. Also, do you always need to line sewers if lifting? Not necessarily. It just depends on the nature of the damage in the sewer. And often, if we are going to lift a sewer, we would want to try and monitor it, possibly. We often work around sewers and water pipes, and we normally just make sure we monitor them to see nothing goes in, and if something does get in, we can remove what gets in there. So it's not necessarily required to repair before treatment. Not in every case, only if the damage is extreme.
Yeah. Gary asked a question about future impact on foundations post-treatment. Would it affect the warranty? The warranty question's probably not for us, Gary. That's more a commercial thing. But in terms of impact on foundations and bearing pressures in the future, Andy, would probably have to.
I think that looks quite a specific question. What our warranty says that if once we give a warranty for a certain project, that if you then go into that same site later on and dig out our polymer, then obviously that might invalidate the warranty. We assume that when we put the polymer in place, it stays in place. If it's then disturbed later by another party, that could undermine its performance.
Excellent. Okay.
That might be what that's about. I'm not sure. We'd have to be asked specifically.
Theodoros, again, if needed to densify backfill loose soil around circular concrete deep shaft to eliminate surface settlements, use of a geopolymer would exert additional pressure on shaft walls, ?
Well, it would do, but probably not. Because it's expansive, there will be an expansive force on the walls of the shaft. But the level of force we're talking about is probably unlikely to cause any structural damage. So that would be a case-by-case analysis, and we would select a polymer that's appropriate for the structure in question.
Yeah.
Okay, so we've done that quite a lot.
Okay, Sanjay asks, currently assessing pairs of semi-detached dwellings where one structure is subsiding away from the other, noted 100 mil drop to party wall, and the party wall 100 mil. Are there any examples of this type of work? We probably have, Sanjay. I think you should just contact us directly. And
we could look at that directly and give you a view as to what we think.
Yeah, it wouldn't be uncommon.
It looks like quite a common problem we often deal with.
Yeah, I mean, we treat thousands of properties every year, so that's no problem. Has this solution been used in the filling of legacy coal workings, and would this be comparable to costs to traditional PFA OPC grouting of workings?
It has been used. I think it comes down to a cost benefit point of view. You may find that the old school way of doing it is more cost effective. It depends on the depth and the volume, really. So,
yeah.
And where we're probably more competitive is where it's not actually practically feasible to get large scale mine filling plant equipment in situ. So short answer yes and no on that one.
Okay. If used for underpinning or other projects where excavations may require into the bulk, can the strengthened soil be broken out?
Yeah, so I mean, we wouldn't recommend if we've put our polymer in place to densify the soil, and then you come out and someone else comes on later and digs it out, that is going to undermine the work that's been done because we assume it remains in situ. Yeah. So then we would have to look at it might have to be redone. After if it has to be removed, it would probably have to be put back again later to get the conditions as they were.
Okay. Mohammed asks, what is the impact of injection on tree roots? I think you might have touched on this, but the minimal impact, Andy.
Yeah, well, attend the next clay webinar. I've got more data on this.
There
And
you
what
go.
I would say is that we've done some recent study on trees where we've done geopolymer where we've measured the health of the tree before geopolymer and after geopolymer. We've actually got some studies done by a specialist on trees, and they showed there was no impact on the health of the tree. So, and even though the treatment is successful, so whatever we do to the trees, it doesn't affect their health.
Yeah.
So I've got there is more information going to come on that in the next clay webinar.
Yeah, right. I'm just going to skip through these very quickly. If at some point you need to demolish a house, is it difficult to remove?
No, it's not. It can
no.
be removed by normal construction equipment.
Yeah. Building Safety Act increased insurance warranty coming to 15 years. Are there any incentives coming? Commercial question, David. I'll come back to you directly on that one. The injection in coarse soils seems to work perfectly. So what about very fine soils with low permeability?
We've got very good examples.
Yeah.
That we've got very good examples of improvements of low permeability clay soils.
Yeah, Simon, email me after this. You'll get my email. I think you get an email once this meeting finishes. So just reply to that. How long does it take for a geopolymer to reach its full strength?
We're talking minutes.
Okay.
It's measured minutes, not hours.
Is there a limit on depth?
Well, yes, there is, but you know, probably 20 to 25 meters is the current limit.
Residential environments, do we work in them? Michael, we do indeed, absolutely. Join the next webinar. If you need more details, email me. And then we've got, what about resistance to chemical attack?
Only very strong acidic or alkaline conditions. I'm talking very low pH, 1s, 2s, or 14s. Some chemical solvents. If you want more details, ask Alistair. I can let you know.
Okay. Manuel, are polymer degradable with oil products?
Generally speaking, not diesel, not petrol. No.
Okay.
So, but some organic specific solvents maybe.
Yeah. What are the polymers used that create the chemical reaction for the expansion?
Well, you'll have to. I don't know. It's a combination of the resin and the hardener.
Yeah.
And the polymer, it's a resin which is based using. Well, it's made out of mainly polyols. If you want to know what they are, some type of hydrocarbon.
SPTs before does every project? Not necessarily every project. It depends which sector and what we're doing, Andrew.
Yeah.
So
it's project specific. The testing is project specific.
Yeah, and then the final question from Yemi. Great presentation. Well, there you go, Andy. Thank you for that. Would a CPD certificate be issued? Yeah, if you need one, reply to the email that you'll get after the meeting, and then I get that sent to the CPD service, who will send you a certificate within 28 days, apparently. So I assume that happens. But that's it. Slightly ran over there, 3 minutes. Look out for an email from me then with a recording of this and the video we missed. If you've got any other questions, please reply to that, and site-specific questions or projects, reply to me, and I can point you in the right direction, whether that's in the UK or Ireland. So I guess that's it. Thanks, Andy. Look at this, a straggler question. Any gas risk? Dominic Horn.
No.
No, there we go. All right, that's it, I think. Thank you, everyone, for joining. Cheers again, Andy. Look out for the next webinar on clay, beginning of December. All right.
Okay, cheers then. Bye.